The sun just grew bigger. Not over millions of years, not in some distant future. It happened last week and you didn't even notice. Right now, as you're watching this, the star that gives us life, the massive burning sphere 93 million miles away, is larger in our sky than it was just a few weeks ago. And here's what makes this truly strange. We're in the middle of winter, the coldest season of the year, the time when we bundle up, when frost covers our windows, when we can see our breath in the air. But the sun, that blazing furnace in space, has actually grown in size. If you could look through a solar-filtered telescope right now and compare it to images from last summer, you'd see the difference. The sun is measurably, observably bigger. This isn't a metaphor. This isn't some poetic way of describing sunrise or sunset. The actual angular diameter of the sun in our sky has increased, and before you think this is some catastrophic event, some sign of solar expansion or cosmic disaster, let me tell you, this happens every single year. Like clockwork, predictable, inevitable. And yet, most people live their entire lives without ever knowing about it. Stay with me, because in the next few minutes we're going to uncover why the sun grows bigger during the coldest part of the year, and what this reveals about our planet's hidden dance through space. Think about that for a moment. The sun appears larger, which means more of its surface is visible to us, which suggests we should be receiving more heat, more warmth, more energy. That's basic logic, isn't it? Bigger sun equals more heat. Closer fire equals warmer hands. But instead, we're shivering. We're wearing layers. We're watching snowfall from grey skies. The thermometer drops and we huddle indoors, while outside that massive star looms larger than it will at any other point this year. Something doesn't add up here. There's a contradiction at the heart of our everyday experience, a paradox written across the sky that most of us never stop to question. We've been taught about seasons, about summer and winter, about why temperatures change throughout the year. We learned it in school, accepted it as fact, and moved on with our lives. But if you actually pause and think about what's happening right now, if you consider the evidence your own eyes could see through the right equipment, you start to realize there's something we're missing. Some piece of the puzzle that doesn't quite fit the simple story we were told. Astronomers know about this. They've been tracking it for centuries, measuring it with increasing precision, calculating it down to the exact minute when this change occurs. They have charts and graphs and orbital mechanics that explain every detail. But this knowledge rarely makes it beyond the walls of universities and observatories. It stays locked away in textbooks and research papers, while the rest of us go about our days, completely unaware that we're living through something extraordinary. Because here's what's really happening. Our entire planet, this massive sphere carrying billions of people, countless species, every mountain and ocean and forest, is moving through space in ways that affect everything we experience. We think of the ground beneath our feet as stable, as fixed. We think of the sun as constant, always the same distance away, always the same size in the sky. But we're wrong, dead wrong. And the evidence is right there, hanging above us, if we only knew where to look and what it means. You probably woke up this morning, glanced outside, maybe noticed it was cold, maybe thought about the weather, and then went on with your routine. You didn't think about the sun's size. You didn't consider that our star might appear different today than it did months ago. Why would you? We trust our perceptions. We trust that what we've always seen is what we'll continue to see. But perception is a tricky thing, especially when the changes are subtle, when they happen gradually, when they require instruments and calculations to detect. And that's exactly what makes this so fascinating. We're standing on a planet that's constantly moving, constantly shifting its relationship to the sun, and we feel none of it. We see none of it with our naked eyes. We go about our daily lives as if we're stationary, as if the cosmos is some distant backdrop that doesn't affect us. But reality is far more dynamic, far more incredible than our limited senses can capture. So before we go any further, before I reveal what's actually causing the sun to grow larger during winter, I want you to do something. If you're curious about the hidden mechanics of our planet, if you want to understand the cosmic choreography that happens every single day above your head, hit that like button right now. Subscribe to this channel, because we're about to embark on a journey through space and time. By the end of this video, you'll never look at the sun the same way again. Drop a comment telling me where you're watching from, because this phenomenon affects every single person on Earth, no matter which hemisphere you call home. And I want to know how many of you are experiencing winter right now, just like I am. while the sun hangs larger in our sky than it will be in 6 months. The question we need to answer is deceptively simple. Why does the sun appear bigger during winter? But the answer is going to take us on an unexpected path through orbital mechanics, through the history of astronomy, through the very geometry of our solar system. We're going to explore measurements and distances, ancient observations and modern calculations. We're going to confront assumptions you didn't even know you had, and by the time we're finished, you're going to understand something that eludes most people their entire lives. Because this isn't just about the sun. This is about the fundamental relationship between Earth and the star that sustains us. It's about the delicate balance of forces that makes our world habitable. It's about the precision and elegance of celestial mechanics, where everything is connected, where nothing is random, where patterns repeat across centuries and millennia with absolute reliability. And it starts with a simple observation. The sun just grew bigger and nobody told you. So let's find out why and what it means for all of us living on this spinning, orbiting, tilting planet we call home. In early January, astronomers around the world pointed their solar-filtered telescopes toward the sun and took careful measurements. They recorded the angular diameter, the apparent size of the sun as seen from Earth. And when they compared those measurements to observations made in early July, they found exactly what they expected. The sun was noticeably larger, not by a dramatic amount, not enough that you could tell just by glancing up at the sky, but measurable, quantifiable, real. The sun's apparent diameter had increased, and the difference was significant enough that even amateur astronomers with decent equipment could detect it. This wasn't some subtle variance within the margin of error. This was a legitimate, observable change in how large the sun appears from our vantage point on Earth. Now, when we talk about the sun appearing larger or smaller, we need to understand what that actually means. The sun itself hasn't changed size. It's not expanding or contracting. It's not somehow growing and shrinking like some cosmic heartbeat. The sun is remarkably stable in its actual physical dimensions. What changes is our distance from it, and distance affects how large objects appear in our field of vision. Think about watching a car drive away from you. The car doesn't shrink, but it appears smaller and smaller as it gets farther away. The same principle applies to the sun. When Earth is closer to the sun, it appears larger in our sky. When Earth is farther away, it appears smaller. Simple geometry, simple optics. But here's where it gets interesting. Earth's distance from the sun changes throughout the year in ways that might surprise you. We measure apparent size in angular degrees, the angle that an object subtends from our viewing position. The sun's angular diameter varies throughout the year by a small but measurable amount. At its largest, the sun spans a slightly greater arc across our sky. At its smallest, that arc contracts. The difference is there, recorded in astronomical data, confirmed by multiple observations across different locations and different instruments. Ancient astronomers noticed something unusual long before they had telescopes or precise measuring equipment. They observed that the sun seemed to move differently across the sky at different times of year. They tracked its path, marked its positions at sunrise and sunset, and they realized that the sun's behavior wasn't perfectly uniform. There were variations, cycles within cycles, patterns that repeated annually but with subtle differences. These early skywatchers didn't have our modern understanding of orbital mechanics. They didn't know about elliptical orbits or gravitational dynamics, but they were meticulous observers and they knew something was changing. They created calendars based on these observations, built monuments aligned to solar positions, and passed down knowledge about the sun's varying journey across the heavens. When telescopes were invented and astronomers could magnify the sun safely, they confirmed what ancient observers had suspected. The sun's apparent size does change, and with increasingly sophisticated instruments, they were able to measure exactly how much it changes and when. They discovered that the variation follows a predictable annual cycle, reaching maximum apparent size in early January and minimum apparent size in early July. This discovery raised obvious questions. Why would Earth be closer to the sun during Northern Hemisphere winter? Why would the sun appear largest when temperatures are coldest? It seemed to contradict everything people assumed about how seasons work. Most of us grow up believing that summer happens when Earth is closer to the sun and winter happens when Earth is farther away. It's an intuitive explanation. It makes perfect sense. And it's wrong. The measurements are unambiguous. Multiple space agencies, observatories, and research institutions track Earth's distance from the sun with extraordinary precision. They use radar, they use spacecraft telemetry, They use mathematical models confirmed by centuries of observation, and all of that data tells us the same thing. Earth reaches its closest approach to the Sun around early January, during the depths of Northern Hemisphere winter. This isn't speculation or theory. This is documented fact, verified and re-verified countless times. You can look up the data yourself. You can examine the measurements from any year you choose. The pattern holds. January brings us closer to the Sun than any other month, and that closeness translates directly into a larger apparent size. But if we're closer to the Sun, why isn't it warmer? That's the question burning in your mind right now, isn't it? It's the obvious contradiction, the puzzle that needs solving. Distance should matter. Proximity to a heat source should result in higher temperatures. That's basic physics. That's everyday experience. Move closer to a fire, you feel warmer. Move away, you feel cooler. So why doesn't this same principle apply to Earth and the Sun? The answer exists, and we're going to get there. But first, we need to understand exactly what's happening with these measurements. We need to appreciate that when astronomers tell us the Sun has grown larger in our sky, they're not speaking metaphorically or approximately. They're sharing precise observational data that reveals something fundamental about our planet's motion through space. Earth doesn't orbit the Sun in a perfect circle. This is crucial. This is the key that unlocks everything else. Most people imagine Earth's orbit as a neat circular path, with the Sun at the centre, and Earth maintaining a constant distance as it travels around. That image is clean and simple and completely wrong. Earth's orbit is an ellipse, a slightly elongated circle, and the Sun isn't at the centre of that ellipse. It's at one of the two focal points offset from the middle. This means that as Earth moves along its orbital path, its distance from the Sun constantly changes. There are times when Earth swings closer to the Sun and times when it arcs farther away. The orbit isn't drastically elliptical. We're not talking about wildly varying distances, but the variation is enough to produce measurable, observable effects, including the change in the Sun's apparent size. In early January, Earth reaches the point in its orbit closest to the Sun. Astronomers have a name for this: perihelion. It's derived from Greek words meaning near and sun. Perihelion is that moment when our planet is at its minimum distance from the star that sustains us. And because we're closer, the Sun appears larger. More of its surface fills our field of vision. The angular diameter increases. 6 months later, in early July, Earth reaches the opposite point in its orbit. We're now at maximum distance from the Sun, a position called aphelion, meaning away from Sun. At aphelion, the Sun appears slightly smaller because we're viewing it from farther away. The angular diameter decreases to its minimum value for the year. The difference in distance between perihelion and aphelion isn't trivial. We're talking about millions of miles of variation. Earth's orbit brings us closer to the Sun by a significant margin during perihelion, then carries us farther away during aphelion. And throughout this journey, the Sun's apparent size waxes and wanes like a slow, predictable tide. But here's what's remarkable. We don't feel this distance change. We don't experience any dramatic shift in temperature or sunlight just because perihelion occurred. The coldest time of year in the Northern Hemisphere coincides with the closest approach to the Sun, and the warmest time coincides with the farthest distance. This seems impossible, contradictory, wrong. And yet it's exactly what happens, year after year, with absolute consistency. So we're left with a deepening mystery. The observations are clear, the measurements are precise. The Sun has grown larger because Earth has moved closer, but the temperature has dropped because we're in winter. Two facts, both true, both verified, and seemingly incompatible. This is the paradox we need to resolve, and the resolution is going to reveal something beautiful about how our planet works. Let's confront this contradiction directly. The Sun is bigger right now. Earth is closer to its star than it will be during summer. More of the Sun's massive surface is visible, filling a larger portion of our sky. And yet, we're cold. Temperatures have plummeted, ice forms overnight, snow blankets the ground in many regions. The warmth we associate with sunlight seems to have vanished, despite the fact that we're actually nearer to the source of that warmth. This makes no intuitive sense. Every instinct, every bit of everyday experience tells us that proximity equals heat. Stand next to a radiator, you warm up. Step away, you cool down. The relationship between distance and thermal energy is something we understand from childhood. It's wired into our basic understanding of how the world works. So when someone tells you that Earth is closest to the Sun during winter, your brain rebels. It searches for explanations, for ways to reconcile this apparent impossibility. Maybe the measurements are wrong. Maybe the scientists made a mistake. But no, the observations have been confirmed too many times by too many independent sources, using too many different methods. The data is solid. Earth really is closer to the Sun in January than in July. The Sun really does appear larger during Northern Hemisphere winter. These aren't disputed facts, they're documented reality. Maybe the Sun produces less energy during winter. Maybe its output varies throughout the year, compensating for the distance change. But that doesn't hold up either. The Sun's energy output is remarkably stable. It's not a variable star that pulses or dims. It's a steady, consistent fusion reactor that has maintained remarkably consistent power output throughout its lifetime. Solar radiation doesn't drop off significantly during any particular season. The Sun doesn't know or care what season it is on Earth. Maybe Earth's atmosphere changes. Maybe we have more cloud cover during winter, blocking sunlight and causing temperatures to drop despite our proximity to the Sun. There's a grain of truth here. Weather patterns do vary seasonally, and cloud cover affects how much sunlight reaches the surface. But this can't explain the global pattern. Southern Hemisphere experiences summer during January, with warm temperatures and long days, while using the same sun that Northern Hemisphere sees. If distance were the primary factor, both hemispheres should experience similar temperatures at the same time, regardless of cloud cover. But they don't. We're missing something fundamental here. Distance clearly isn't the dominant factor controlling seasons, but we haven't yet identified what is. There's another variable in play, something more powerful than the millions of miles between Earth and Sun, something that overrides the simple geometry of proximity and heat. Think about how sunlight reaches Earth. It travels across space, crosses the gap between star and planet, enters our atmosphere and strikes the surface. That journey is the same whether Earth is at perihelion or aphelion. The light doesn't fundamentally change, the energy doesn't transform. But something about how that sunlight interacts with our planet must be different, because the effects are dramatically different. Consider two scenarios. In one, you hold a flashlight directly above a table pointing straight down. The beam creates a bright, concentrated circle of light. In the other, you angle that same flashlight, pointing it at the table from the side. Now the beam spreads out, covering a larger area but with less intensity at any given point. Same flashlight, same bulb, same distance from the table. But the angle changes everything. The direct beam is intense and focused. The angled beam is diffuse and weak. This analogy holds a clue to our mystery. The angle at which sunlight strikes Earth might matter more than the distance it travels to get here. And if that's true, if angle trumps distance in determining how much heat we receive from the Sun, then we need to understand what controls that angle. What determines whether sunlight hits Earth directly or at a slant? What varies throughout the year in a way that would explain why winter is cold despite the Sun being larger and closer? The answer isn't in Earth's orbit around the Sun. The answer is in Earth itself, in how our planet is oriented as it makes that orbit. Because Earth doesn't travel through space standing straight up and down. It's tilted, leaning, canted at an angle relative to its orbital plane. And that tilt, that seemingly small geometric detail, changes everything. Imagine Earth as a spinning top, rotating on its axis once every 24 hours, giving us day and night. But unlike a top standing perfectly vertical, Earth's axis is tilted. The angle is substantial, a noticeable lean that persists year-round. As Earth orbits the Sun, it maintains this tilt, keeping its axis pointing in the same direction in space. This is called axial tilt, and it's the key to understanding why winter is cold even when we're close to the Sun. During Northern Hemisphere winter, the North Pole tilts away from the Sun. This means that sunlight strikes the Northern Hemisphere at a steep angle, spreading out over a larger area and delivering less energy per square foot of surface. Days are short because the tilted planet keeps the Northern Hemisphere partially turned away from the Sun during most of its daily rotation. Nights are long, giving heat time to radiate away into space. The Sun may be closer, but it's hitting us at a poor angle, its energy dispersed and weakened by geometry. Meanwhile, the Southern Hemisphere tilts toward the Sun during this same period. Sunlight strikes more directly, concentrating its energy, warming the surface efficiently. Days are long, nights are short, and temperatures rise. Southern Hemisphere experiences summer in January, not because Earth is closer to the Sun, but because the tilt points that hemisphere toward the Sun, giving it direct concentrated sunlight despite the millions of miles involved. 6 months later, Earth has travelled halfway around its orbit. The distance to the Sun has changed. We're now farther away at aphelion, and the Sun appears slightly smaller in the sky. But the critical factor isn't distance, it's tilt. Now the North Pole tilts toward the Sun. Northern Hemisphere receives direct sunlight, concentrated and intense, while Southern Hemisphere tilts away, receiving angled, dispersed light. Northern summer and southern winter arrive, driven by orientation, not by distance. This is the resolution to our paradox. Distance affects how large the Sun appears, but tilt determines how much heat we actually receive. And tilt is far more powerful than distance when it comes to controlling temperature. The angle at which sunlight strikes Earth overwhelms the effect of being a few million miles closer or farther from the Sun. Geometry beats proximity. Orientation matters more than distance. So we find ourselves in the strange situation where the Sun grows larger in our sky at precisely the time when it heats us least effectively. The two factors pull in opposite directions, but tilt wins. Earth's lean, its persistent angle relative to its orbital plane, dictates our seasons while distance plays a supporting role, noticed by telescopes but barely felt by thermometers. And this explains why ancient astronomers were puzzled. They could see patterns in the Sun's motion. They could detect variations in its path across the sky. But without understanding orbital mechanics and axial tilt, they couldn't explain why the Sun's behavior didn't match the temperature changes they experienced. They were observing real phenomena without the conceptual framework to interpret what they saw. Now we have that framework, and the paradox dissolves into elegant logical mechanics. But that doesn't make it any less fascinating. Before we go deeper into the mechanics of what's really happening, we need to clear away some misconceptions. Because when people first hear that the Sun has grown larger in the sky, their minds often jump to explanations that sound plausible but aren't correct. Let's address these false paths, not because I think you believe them, but because eliminating wrong answers helps us appreciate the right one. First, this has nothing to do with climate change. I know that whenever someone mentions unusual solar behavior or changes in Earth's climate patterns, the immediate association is with global warming or climate shift. But the Sun growing larger during winter is not a new phenomenon caused by human activity or recent environmental changes. This has been happening since Earth first settled into its current orbit billions of years ago. Ancient dinosaurs experienced this same cycle. Early humans saw the same patterns. Medieval astronomers recorded the same observations. This is not a modern crisis or a recent development. It's a fundamental characteristic of how our planet moves through space. Climate change is real and significant, but it operates on different timescales and through different mechanisms. It's about atmospheric composition, greenhouse gases, heat retention, and feedback loops. It's not about Earth's orbital distance from the Sun suddenly changing. When we talk about the Sun appearing larger in January, we're discussing orbital mechanics that have been stable for eons, not climate dynamics that are shifting due to human influence. Second, the Sun itself is not expanding. There's no solar crisis here. The Sun isn't growing, swelling, entering a different phase of its stellar life cycle. Stars do expand as they age, eventually becoming red giants that consume inner planets. But that's a process that takes billions of years, and our Sun is only about halfway through its stable phase. The changes we're discussing happen over months, not millennia. The Sun's physical size remains constant while Earth's distance from it varies. This is entirely about our motion, not solar evolution. When the Sun appears larger, it's not because the star has grown. It's because we've moved closer to it. The distinction matters. One scenario would suggest cosmic instability. The other simply describes orbital mechanics. The Sun is fine. It's burning hydrogen, fusing elements, radiating energy exactly as it has for billions of years. Nothing about the Sun's behavior or structure has changed. Only our viewpoint has shifted. Third, these measurements are not errors or illusions. Some skeptics might wonder if the apparent size change is just a trick of atmospheric conditions, a distortion caused by Earth's air, or perhaps a measurement inconsistency between different instruments. But astronomers account for atmospheric effects. They calibrate their instruments meticulously. They cross-reference observations from multiple locations and multiple telescopes. They use spacecraft data that bypasses Earth's atmosphere entirely. The measurements are robust and reliable. The Sun's apparent size change is tiny compared to optical illusions we sometimes see, like the Moon appearing huge on the horizon versus smaller overhead. That Moon illusion is perceptual, psychological, not a real change in angular size. But the Sun's variation between perihelion and aphelion is actual, measurable, consistent across all observation methods. It's not an illusion. It's not an artifact of measurement technique. It's genuine geometric reality captured by physics and mathematics. Fourth, this isn't some newly discovered phenomenon that scientists just figured out. The knowledge that Earth's orbit is elliptical dates back centuries. Johannes Kepler described the elliptical nature of planetary orbits in the early 1600s. Isaac Newton explained the gravitational mechanics that produce these ellipses. Astronomers have been calculating perihelion and aphelion dates with high precision for generations. This isn't breaking news or cutting-edge research. It's well-established fundamental astronomy. What is new is that most people never learn this fact. It gets lost somewhere between elementary school science and everyday life. We learn that Earth orbits the Sun. We learn about seasons, but the specific details about elliptical orbits and perihelion often don't stick. So when someone hears about it for the first time as an adult, it feels like a revelation, like hidden knowledge. But it's not hidden. It's just not commonly discussed outside academic contexts. Fifth, the distance variation isn't dramatic enough to cause catastrophic effects. Some might worry that swinging millions of miles closer to the Sun could be dangerous, could expose us to harmful radiation or excessive heat. But the percentage change in distance is relatively small. Earth's orbit is only slightly elliptical. The variation in solar radiation that reaches Earth due to this distance change is minor, far less significant than the variation caused by axial tilt. We're not in danger at perihelion. We don't get mysteriously irradiated. The difference in solar energy received is measurable but not extreme. Engineers and scientists who plan space missions account for these orbital variations. Satellites and spacecraft need to adjust for Earth's changing position, but these are routine calculations, not emergency responses to cosmic threats. The elliptical orbit is normal, stable, and entirely safe. It's been this way for billions of years, and it will continue for billions more. Sixth, this phenomenon affects both hemispheres, just differently. It's not that Northern Hemisphere experiences perihelion while Southern Hemisphere doesn't. Both hemispheres are on the same planet, orbiting together, reaching perihelion at the same moment in early January. The Sun appears larger to observers in both hemispheres simultaneously, but the seasonal effect, the temperature impact, is opposite because the hemispheres tilt in opposite directions. When the north tilts away from the Sun, the south tilts toward it. Same orbit, same perihelion, different seasonal experiences. This global consistency is important. We're not talking about a localized phenomenon or a regional variation. We're describing a planetary scale dynamic that affects everyone on Earth in a coordinated way. The orbital mechanics don't care about geography or latitude. They apply universally, creating patterns that span the entire globe. By eliminating these false paths, we've narrowed our focus to what actually matters, the interplay between Earth's elliptical orbit and its axial tilt. These two factors, working together, create the seasonal cycle we all experience. Distance varies throughout the year, affecting the Sun's apparent size but only marginally affecting temperature. Tilt varies throughout the year relative to the Sun's position, dramatically affecting how sunlight strikes each hemisphere, and therefore controlling temperature in powerful ways. We're not dealing with mysteries or anomalies. We're dealing with physics, with geometry, with the predictable consequences of a tilted planet following an elliptical path around its star. And now that we've cleared away the misconceptions, we can appreciate the elegant mechanics of what's really happening above our heads every single day. So here's the answer you've been waiting for, the reason why the Sun appears larger during the coldest months, the explanation that resolves the paradox and illuminates how our planet actually works. In early January, Earth reaches a point in its orbit called perihelion, the moment when our planet comes closest to the Sun. And because we're closer, because the distance between Earth and its star has decreased by millions of miles compared to 6 months earlier, the Sun appears larger in our sky. That's it. That's the core truth at the heart of this entire mystery. But don't let the simplicity of that statement fool you. The implications are vast and the mechanics behind it are beautiful in their precision. Let's unpack what perihelion really means and why it happens. Earth's orbit around the Sun is not a perfect circle. I mentioned this earlier, but now we need to really understand it. When you imagine a planet orbiting a star, your mind probably pictures a circular path with the star at the center and the planet maintaining constant distance as it loops around. It's a tidy mental model, easy to visualize, and used in countless simplified diagrams. But it's not reality. Planets orbit in ellipses, elongated circles with two focal points instead of a single center. The Sun sits at one of these focal points, not at the center of the ellipse. This means that as a planet travels along its orbital path, it's sometimes closer to the Sun and sometimes farther away. The orbit isn't wildly stretched or dramatically elongated. Earth's orbit is close to circular, but not quite. The deviation from perfect circularity is enough to produce measurable, observable effects. This elliptical shape is a direct consequence of gravity and motion. When Earth formed from the swirling disk of material around the young Sun, it settled into an orbit determined by its speed and the gravitational pull of the Sun. The balance between these forces produces an ellipse. If Earth were moving at exactly the right speed for a perfectly circular orbit, and if no other forces ever disturbed it, then yes, it would maintain constant distance from the Sun. But space is dynamic. Other planets exert gravitational tugs. The early solar system was chaotic. Earth's orbit ended up slightly elliptical, and it's stayed that way ever since. The point of closest approach in this elliptical orbit is perihelion. It occurs once per year, always in early January. The exact date and time vary slightly year to year due to complex gravitational interactions with other planets, but it's always within a narrow window in early January. At perihelion, Earth is at its minimum distance from the Sun, having followed its orbital path around to the point where it swings nearest to its star. 6 months later, Earth reaches the opposite side of its orbit, the point farthest from the Sun. This is called aphelion, and it occurs in early July. At aphelion, Earth is at maximum distance from the Sun, having travelled around to the far end of its elliptical path. The difference in distance between perihelion and aphelion is substantial, millions of miles of variation that directly affects how large the Sun appears. Now here's what makes this fascinating. That distance variation is far less important for determining Earth's temperature than you'd think. Yes, being closer to the Sun means receiving slightly more solar radiation per unit area. At perihelion, Earth receives a bit more energy from the Sun than it does at aphelion. You'd expect that extra energy to warm us up, to make January temperatures higher than July temperatures. But it doesn't work that way, and the reason is that Earth's axial tilt overwhelms the distance effect. Remember our tilted planet leaning at an angle as it orbits. That tilt doesn't change direction as Earth moves through its orbit. Earth's axis points toward the same spot in space throughout the year, like a compass needle always pointing north. This constancy of tilt direction means that different hemispheres tilt toward or away from the Sun at different points in the orbit. During early January, when Earth reaches perihelion and comes closest to the Sun, the northern hemisphere happens to be tilted away from the Sun. This is not a coincidence of timing that happens to align this year. It happens every year. It's built into the geometry of Earth's orbit and rotation. Perihelion occurs during northern winter, not by chance, but by the persistent pattern of Earth's motion. So at the very moment when Earth is nearest to the Sun, when you might expect northern hemisphere to be warmest, the tilt has pointed the northern hemisphere away. Sunlight strikes at a steep angle, glancing across the surface rather than beating down directly. The Sun tracks a low arc across the sky, spending less time above the horizon each day. Nights are long, days are short, and temperatures drop despite the reduced distance to the Sun. Meanwhile, the southern hemisphere tilts toward the Sun during this same perihelion moment. Down there it's summer. The Sun climbs high in the sky. Sunlight strikes nearly overhead, concentrated and intense. Days stretch long into evening. And because Earth is at perihelion, receiving maximum solar energy, southern hemisphere summer is actually slightly more intense than northern hemisphere summer 6 months later. The combination of favourable tilt and close proximity makes January summer in the southern hemisphere the most energetic, most sun-drenched season on Earth. 6 months later, in early July, Earth reaches aphelion. We're now farther from the Sun than at any other point in the year. The Sun appears slightly smaller in the sky. Solar energy reaching Earth per unit area is minutely reduced. But now the northern hemisphere tilts toward the Sun. We get summer, direct sunlight, long days, warm temperatures, and the southern hemisphere tilts away, experiencing winter despite the planet being at maximum distance from the Sun. The pattern is clear. Tilt dominates temperature, distance dominates appearance. The Sun looks bigger at perihelion because we're closer, but we're colder in the northern hemisphere because we're tilted away. The Sun looks smaller at aphelion because we're farther, but we're warmer in the northern hemisphere because we're tilted toward. The two factors operate independently, pulling in different directions, and tilt wins the battle for seasonal temperature control every single time. This is not a new discovery. This is not some recent insight that overturns previous understanding. Astronomers have known about perihelion and aphelion for centuries. They've calculated the dates with precision. They've measured the distance variations. They've understood the relationship between tilt and seasons. But somehow this knowledge doesn't filter into common awareness. Most people go their entire lives without learning that Earth is closest to the Sun during northern winter. It's a gap in our collective understanding, a missing piece of information that, once learned, reframes how we think about our planet. Because here's what perihelion really means. Earth is not on a fixed track. We're not maintaining some constant, unchanging relationship with the Sun. We're in motion, constantly shifting position, constantly changing our distance from the star that sustains us. Every day, that distance is different than it was the day before. Sometimes we're closing in, sometimes we're pulling away, always following the elliptical path that gravity and momentum have carved out for us. And we feel none of this motion. We stand on solid ground, watching the Sun rise and set, completely unaware that we're riding a planet through space at tremendous speed, sweeping around an ellipse that brings us millions of miles closer and then millions of miles farther from a massive nuclear furnace. The scale of this motion is incomprehensible in everyday terms, yet it's absolutely real, absolutely constant, absolutely fundamental to our existence. Perihelion is not just an astronomical term. It's a moment of cosmic alignment, a point in space and time when Earth and Sun come together in their closest annual embrace. And it happens every single year, like clockwork, predictable down to the minute. You can look up the exact date and time of perihelion for any year in the future. You can calculate where Earth will be in its orbit decades from now. The mechanics are that reliable, that precise, that unchanging. And here's something remarkable. The date of perihelion shifts very slowly over thousands of years. Earth's orbit doesn't stay perfectly stable forever. Gravitational interactions with other planets, particularly Jupiter, cause subtle changes in the orbit's orientation over long timescales. Currently, perihelion occurs in early January. But thousands of years ago it occurred at a different time of year, and thousands of years in the future it will shift again, gradually migrating around the calendar like a slow tide. This means that the alignment between perihelion and northern winter is not permanent. It's not some eternal cosmic law. It's a temporary configuration, stable for millennia but not forever. There will come a time, far in the future, when perihelion occurs during northern summer instead of winter. When that happens, northern summers will be slightly more intense than they are now, and southern summers will be slightly milder. The effect will be subtle but real, another reminder that nothing in the cosmos is truly static. But for now, for your lifetime and mine, for centuries past and centuries to come, perihelion occurs in early January, and every January Earth swings closest to the Sun. The Sun appears largest in our sky. A northern hemisphere experiences winter, while southern hemisphere basks in summer heat. It's a dance of geometry and gravity, tilt and distance, played out on a planetary scale with absolute reliability. So when I say the Sun just grew bigger, what I'm really telling you is that Earth just reached perihelion. We've completed another orbit. We've travelled billions of miles through space, circling our star, and we've arrived back at the point of closest approach. The Sun hasn't changed, Earth's orbit hasn't changed, but our position has changed, and that changes everything about how we see the star that gives us life. This is the revelation. This is the answer. Perihelion explains why the Sun appears larger during winter, and axial tilt explains why winter is cold despite that proximity. Two separate factors, operating simultaneously, creating the seasonal pattern we all experience. And now you know something that most people never learn. The Sun's apparent size and Earth's temperature are controlled by different mechanisms, and understanding both gives you a glimpse into the elegant machinery of our solar system. Now that we understand perihelion, let's zoom out and see the full picture of Earth's journey around the Sun. Because this isn't just about one moment in January, this is about a continuous dance, a year-long orbital waltz that Earth performs with precision and grace, carrying all of us along for the ride. Imagine Earth's orbit as a racetrack, but instead of a circle, it's an ellipse. At one end of this ellipse, we have perihelion, the point of closest approach. At the opposite end, 6 months away, we have aphelion, the point of greatest distance. And connecting these 2 points is the orbital path that Earth follows, curving smoothly through space, pulled by the Sun's gravity, propelled by its own momentum. Earth doesn't travel this orbit at constant speed. This is another beautiful consequence of orbital mechanics. When Earth is closer to the Sun, at perihelion, gravity pulls harder. The planet accelerates, moving faster along its orbital path. When Earth is farther from the Sun, at aphelion, gravity's pull weakens slightly. The planet slows down, coasting through that portion of its orbit at a more leisurely pace. This variation in orbital speed is subtle but measurable. Earth moves several thousand miles per hour faster at perihelion than it does at aphelion. The difference isn't enough to notice from our perspective on the surface. We don't feel any acceleration or deceleration, but spacecraft navigators and satellite operators account for these speed changes when planning missions and calculating trajectories. The variation is real and significant for precision work. So in early January, Earth is not only closest to the Sun but also moving fastest in its orbit. We're racing through space at peak velocity, whipping around the inner portion of our elliptical path. By early July at aphelion, we've slowed down, taking our time as we round the far side of the orbit before beginning the gradual acceleration back toward perihelion. This speed variation has practical consequences. Because Earth moves faster during the Northern Hemisphere winter months, those months are actually slightly shorter than summer months. The calendar evens this out by averaging day lengths, but if you measured the time between equinoxes and solstices, you'd find that northern winter is a bit briefer than northern summer. Earth spends less time in the perihelion half of its orbit, because it's moving faster through that section. Winter passes a little quicker, summer lingers a little longer, all because of orbital mechanics we can't perceive directly. Now let's talk about the energy budget. At perihelion, Earth receives more solar radiation than at any other time of year. The Sun is closer, so its light is slightly more intense. The increase isn't dramatic, but it's measurable. Earth receives several % more energy from the Sun at perihelion than it does at aphelion. This extra energy arrives during northern winter and southern summer, affecting both hemispheres but in very different ways. For the northern hemisphere, tilted away from the Sun at perihelion, that extra solar energy isn't enough to overcome the geometric disadvantage of the tilt. Sunlight hits at such a poor angle that even the boost from proximity doesn't warm us significantly. Winter remains cold despite the increased energy flux. The tilt penalty outweighs the distance benefit. For the southern hemisphere, tilted toward the Sun at perihelion, the extra energy combines with favourable geometry to create the most intense summer conditions on Earth. Southern summer receives both the advantage of direct sunlight and the advantage of close proximity. This makes January one of the warmest months globally, with southern continents and oceans absorbing maximum solar energy. Australia swelters, South America bakes, Antarctica, even with its ice sheets, receives intense 24-hour sunlight near the South Pole. 6 months later at aphelion, the situation reverses. Earth is now farther from the Sun, receiving slightly less solar energy. But the northern hemisphere tilts toward the Sun, gaining the geometric advantage that delivers direct concentrated sunlight. Northern summer arrives, though it's ever so slightly milder than southern summer was at perihelion. The distance penalty slightly reduces the energy we receive, but tilt still provides enough of an advantage to make July warm across the northern continents. Meanwhile, southern hemisphere tilts away at aphelion, experiencing winter while also being at maximum distance from the Sun. Southern winter combines tilted away geometry with reduced solar energy from increased distance. But again, tilt dominates. The angle at which sunlight strikes matters far more than the few % reduction in energy from being a bit farther from the Sun. This annual cycle has been happening for as long as Earth has had its current orbital configuration. Billions of years, countless orbits, Earth swinging from perihelion to aphelion and back again, year after year, creating the seasonal rhythm that life on this planet has adapted to. Plants time their growth cycles to these seasons. Animals migrate, hibernate, or breed based on seasonal cues. Human civilizations developed agriculture around seasonal patterns. Everything alive on Earth has been shaped by this orbital dance. And it's not just life that responds. Earth's oceans and atmosphere participate in this cycle as well. Ocean currents shift with seasonal temperature changes. Atmospheric circulation patterns evolve throughout the year. Ice sheets grow and shrink. River flows vary. Weather systems strengthen or weaken. All of these planetary scale processes are influenced by the seasonal cycle, which in turn is driven by the interplay of tilt and orbital position. The precision of this system is remarkable. Earth completes one full orbit in just over 365 days. That number is so consistent that we base our entire calendar on it. We've divided the year into months and weeks, marked solstices and equinoxes, created holidays and agricultural schedules, all synchronized to Earth's orbital period. The reliability of this motion allows us to predict seasons years in advance, to know exactly when spring will arrive or when winter will set in, to plan our lives around cosmic rhythms we've come to trust absolutely. But here's what's truly awe-inspiring. We're completely unaware of this motion as it happens. You're orbiting the Sun right now, at this very moment, travelling thousands of miles per hour through space. You're part of this grand cosmic choreography, dancing around a star, tilting and spinning and moving through an ellipse that stretches across millions of miles, and you feel nothing. No wind in your face from the orbital velocity, no shift in gravity as distance changes, no sensation of rotation as Earth spins on its axis. Nothing. The scale of cosmic motion is so vast and the forces so perfectly balanced that we experience only the consequences, never the motion itself. We see sunrise and sunset, the visible result of Earth's rotation, but we don't feel the spin. We experience changing seasons, the result of tilt and orbit, but we don't sense the motion through space. We live on a planet in constant movement, and we perceive it as solid, stable, unchanging ground beneath our feet. This disconnect between reality and perception is worth pondering. We trust our senses, we believe what we see and feel, but our senses evolve to deal with the immediate environment, not cosmic scale phenomena. They tell us Earth is still and the Sun moves across the sky. They tell us we're stationary while everything else rotates around us, and for everyday survival, that perspective works fine. But it's not true. The deeper truth is that we're the ones moving, spinning, orbiting, hurtling through space on a tilted planet, following an elliptical path around a star. Ancient astronomers struggled with this realization. When they first proposed that Earth orbits the Sun rather than the Sun orbiting Earth, they faced skepticism and resistance. How could Earth be moving if we feel no motion? How could we be flying through space without any sensation of movement? It seemed impossible, counterintuitive, wrong. But careful observation and mathematical reasoning revealed the truth, and eventually humanity accepted that our perceptions, while useful, don't reveal the full reality of our cosmic situation. Today, we have spacecraft and satellites that can photograph Earth from space, showing us as a blue marble hanging in blackness, clearly a planet among planets, obviously moving through space just like any other celestial body. We have the mathematics and observations that precisely describe our orbit. We can calculate where Earth will be in its elliptical path on any given date. We've sent missions to other planets, navigating through the solar system using the same orbital mechanics that govern Earth's motion. The evidence is overwhelming and undeniable, and yet knowledge of perihelion and aphelion remains obscure. Most people never learn these terms. The fact that Earth is closest to the Sun during northern winter surprises nearly everyone who hears it for the first time. This gap between scientific knowledge and public awareness is curious. We've known about elliptical orbits for centuries, but somehow that information doesn't permeate into common education or casual conversation. It stays locked in textbooks and astronomy courses, rarely making its way into everyday understanding. Perhaps that's why this revelation feels so powerful when you finally encounter it. You've been living through perihelion and aphelion your entire life, experiencing the seasonal consequences, never knowing the cosmic geometry behind it all, and now you do. Now you understand that you're part of a planetary scale dance that's been performing the same routine for eons and will continue long after you're gone. So we've established that Earth is closest to the Sun during northern winter and farthest during northern summer. We've explained that this is due to Earth's elliptical orbit, with perihelion in January and aphelion in July. But the lingering question remains, why doesn't distance matter more? Why does a few million miles of separation play second fiddle to a 23-degree tilt? What makes angle so much more powerful than proximity when it comes to controlling temperature? The answer lies in how energy from the sun actually reaches and heats Earth's surface. Solar radiation travels through space as electromagnetic waves, carrying energy across the void between star and planet. When that radiation reaches Earth, it interacts with the surface, transferring energy, warming the ground and oceans and atmosphere. But the efficiency of this energy transfer depends critically on the angle at which the radiation strikes. Imagine you're holding a flashlight in a dark room, shining it at a wall. When you point the flashlight directly at the wall, perpendicular to the surface, the beam creates a small, bright circle. All the light energy concentrates in that area, making it intensely illuminated. Now tilt your flashlight, pointing it at an angle. The beam spreads out, covering a larger area on the wall. The same amount of light from the bulb now distributes across more space, so any particular spot on the wall receives less light. The brightness decreases because the energy disperses. This is exactly what happens with sunlight striking Earth. When the sun is high in the sky, nearly overhead, its rays hit the surface at close to a 90-degree angle. The energy concentrates on a small area, heating it efficiently. Each square foot of ground receives a full measure of solar energy. But when the sun is low in the sky, near the horizon, its rays strike at a steep angle, glancing across the surface. The same beam of sunlight now spreads across a much larger area, diluting its energy. Each square foot of ground receives only a fraction of the energy it would get from overhead sun. Earth's axial tilt determines the angle at which sunlight strikes each hemisphere throughout the year. During summer, your hemisphere tilts toward the sun. The sun climbs high in the sky at midday, sometimes nearly overhead depending on your latitude. Sunlight pours down at favourable angles, concentrating energy on the surface. During winter, your hemisphere tilts away from the sun. The sun never rises far above the horizon, even at noon. It hangs low in the southern or northern sky, depending on which hemisphere you're in. Sunlight arrives at steep angles, spreading out, delivering far less energy per unit area. The difference is dramatic. A square metre of ground at the equator, where the sun passes directly overhead, can receive more than twice as much solar energy as a square metre at high latitudes where the sun always stays low in the sky. That's not a subtle variation. That's a massive difference in energy delivery, driven entirely by geometry, by the angle at which light strikes the surface. Distance also affects how much energy reaches Earth, but to a far smaller degree. At perihelion, Earth is several million miles closer to the Sun than at aphelion. That closer position increases the intensity of solar radiation by a few percent. It's a measurable difference, detected by instruments, but it's nowhere near as significant as the difference created by angle. A few percent increase from proximity simply cannot compete with a doubling or halving of energy delivery caused by tilt. There's another factor at play: day length. When your hemisphere tilts toward the sun, not only does the sun climb higher in the sky, but it also stays above the horizon longer. Summer days stretch, giving the surface more hours of solar heating. Winter days shrink, limiting the time available for the sun to deliver energy. This day-length variation compounds the angle effect, further amplifying the difference between summer and winter. At extreme latitudes, near the poles, this effect becomes most pronounced. During summer, the sun never fully sets for weeks or months, circling the sky continuously. During winter, the sun never rises, leaving the region in darkness for equally long periods. This is a direct consequence of Earth's tilt. The axis points toward the sun during summer, keeping the pole in constant sunlight. The axis points away during winter, plunging the pole into prolonged night. Even at mid-latitudes where most people live, day length varies significantly between seasons. Summer days might last 16 hours while winter days shrink to 8. That's double the sunlight hours, double the opportunity for the sun to heat the surface. And when you combine longer days with higher sun angles, you get a compounding effect that creates strong seasonal temperature swings. Now consider that distance variation between perihelion and aphelion amounts to a few percent change in solar intensity, affecting both hemispheres equally and simultaneously. Meanwhile, tilt creates angle variations that can double or halve energy delivery, affecting hemispheres oppositely. Tilt also creates day-length variations that can double or halve exposure time. When you stack these factors, it becomes obvious why tilt dominates. The percentage change in distance is small. The percentage change in effective solar energy due to angle and day length is enormous. Tilt wins because it produces larger variations in energy delivery than distance does. It's that simple and that profound. There's also a question of consistency. Earth's tilt remains constant as the planet orbits. The axis always points in the same direction in space. This constancy means that the tilt effect is systematic and predictable. During one half of the orbit, the northern hemisphere tilts toward the sun and experiences summer, while the southern hemisphere tilts away and experiences winter. During the other half, the situation reverses. The tilt creates a perfect alternating pattern of seasons. Distance variation, on the other hand, affects both hemispheres simultaneously in the same way. At perihelion, both hemispheres are closer to the sun. At aphelion, both are farther. If distance were the primary driver of seasons, both hemispheres would experience summer at the same time when Earth is closest to the sun, and both would experience winter when Earth is farthest. But that's not what happens. Instead, hemispheres have opposite seasons at the same time, a pattern that can only be explained by tilt, not by distance. This hemispheric opposition is your proof that tilt matters more than distance. If you're experiencing winter in New York while someone in Sydney is experiencing summer, and both of you are the same distance from the sun at that moment, then clearly something other than distance is controlling temperature. That something is tilt, is angle, is the geometric relationship between Earth's axis and the sun's position in the sky. Ancient Greek scholars understood some of this. They noticed that the sun's path across the sky changed throughout the year, rising and setting at different points on the horizon, climbing to different maximum heights at noon. They didn't have modern concepts of tilt and orbit, but they recognized that the sun's behavior varied seasonally in ways that correlated with temperature. They were observing the effects of axial tilt without understanding the cause. Later, as astronomy advanced and the heliocentric model took hold, scientists realized that Earth's tilt was the key to seasons. They could calculate exactly how much the angle of sunlight would vary throughout the year based on Earth's tilted axis and its orbit around the sun. They could predict day lengths for any latitude and any date. They could explain why the tropics stay warm year-round, why polar regions experience extreme seasonal variation, why temperate zones have moderate but distinct seasons. All of this knowledge flows from understanding that Earth spins on a tilted axis while orbiting the sun. That tilt, that 23-degree lean, is the master control for Earth's climate zones and seasonal patterns. It determines where deserts form and where rainforests thrive. It influences ocean currents and atmospheric circulation. It shapes the distribution of life across the planet's surface. And remarkably, that tilt has remained relatively stable for millions of years. Earth's axis wobbles slightly over long timescales, a motion called precession, but the angle of tilt stays within a narrow range. This stability is crucial for climate stability. If Earth's tilt varied wildly, seasonal patterns would become unpredictable, making it difficult for complex life to adapt. The fact that our tilt is stable, and that it falls in the range of 20 to 25 degrees, creates seasonal variation strong enough to drive ecological diversity, but not so extreme as to make the planet uninhabitable. So when I tell you that tilt wins over distance, I'm not just explaining a quirk of astronomy. I'm describing one of the fundamental factors that makes Earth habitable, that creates the environmental conditions under which life flourishes. The tilt matters, the angle matters. The way sunlight strikes our world matters more than almost anything else when it comes to temperature and climate. And now you understand why the sun can appear larger during winter without making us warmer. You understand that proximity isn't everything, that geometry can overwhelm distance, that a simple tilt has more power over our weather than millions of miles of cosmic space. It's a lesson in how the universe works, a reminder that intuition can mislead us, and careful observation combined with mathematical reasoning reveals truths that our senses alone would never discover. Now that we've unraveled the core mystery, let's explore some of the fascinating implications and connected phenomena that most people never consider. Because perihelion and Earth's tilted orbit don't exist in isolation, they ripple outward, affecting climate patterns, space exploration, even the length of the year itself in ways that challenge our assumptions about how stable and predictable our world really is. First, let's talk about the southern hemisphere summer. We've mentioned that southern summer occurs during perihelion, when Earth is closest to the sun. This means the southern hemisphere experiences what should theoretically be the most intense summer possible on Earth, combining favourable tilt with maximum proximity. And indeed, measurements confirm that southern hemisphere summer is slightly warmer on average than northern hemisphere summer, though the difference is subtle because other factors like ocean distribution and landmass affect regional temperatures. But here's what's interesting. Despite this theoretical advantage, southern summers don't dominate Earth's climate in obvious ways. The reason is that the southern hemisphere contains far more ocean than the northern hemisphere. Oceans have enormous heat capacity, absorbing and storing thermal energy without dramatic temperature spikes. So even though southern summer receives maximum solar energy, much of that energy goes into warming vast expanses of water, moderating the temperature increase. The land areas in the southern hemisphere, particularly Australia and parts of South America and Africa, do experience intense heat during summer, but the global ocean acts as a buffer, spreading and storing that energy. Northern hemisphere summer, occurring at aphelion when Earth is farthest from the Sun, receives slightly less total solar energy. But the northern hemisphere has much more land mass, and land heats up faster than water, so northern summers can produce extreme heat waves over continental areas even with the distance disadvantage. This interplay between orbital mechanics and geographic distribution creates complex climate patterns that can't be explained by perihelion and tilt alone. Next, consider Earth's orbital speed. We mentioned that Earth moves faster at perihelion and slower at aphelion. This speed variation means that Earth spends less time in the perihelion portion of its orbit and more time in the aphelion portion. The seasons aren't equal in length. Northern hemisphere winter occurring around perihelion when Earth is moving fastest is actually shorter than northern summer. The difference is just a few days, but it's real. Winter passes a bit more quickly because Earth is racing through that portion of its orbit. This asymmetry affects everything from agricultural planning to seasonal business cycles. Growing seasons in the northern hemisphere benefit from slightly longer summers. Energy consumption patterns shift because winter heating periods are briefer than they would be if the orbit were circular. These are subtle effects, barely noticeable year to year, but they accumulate over time and influence long-term climate statistics. Now let's think about space missions. When engineers plan spacecraft trajectories, especially missions to other planets, they account for Earth's position in its orbit. Launching during certain times of year can provide advantages or disadvantages depending on where you want to go. If you're launching a mission to Mars, you want to time your departure when Earth and Mars are favourably aligned, which depends on both planets' orbital positions. Perihelion and aphelion factor into these calculations because they affect Earth's orbital velocity, which in turn affects how much energy is required to escape Earth's gravity and reach your destination. Satellite operators also care about perihelion and aphelion. Earth's slightly elliptical orbit means that the planet's gravitational field, as experienced by satellites in high orbits, varies subtly throughout the year. Satellites need occasional adjustments to maintain precise orbits, and the timing of those adjustments accounts for Earth's changing orbital characteristics. Even GPS satellites, which require extraordinary positional accuracy, factor in orbital mechanics when calculating and broadcasting their positions to receivers on the ground. There's also a fascinating historical dimension. Ancient civilizations tracked solar and lunar cycles with impressive precision, often encoding that knowledge in calendars, monuments, and agricultural practices. Some of these cultures may have noticed subtle variations in the sun's behaviour throughout the year, though they lacked the conceptual framework to explain perihelion and aphelion. Stone circles, temple alignments, and astronomical texts from ancient Egypt, Mesopotamia, and Mesoamerica show sophisticated understanding of solar cycles, suggesting that even without modern tools, careful observers could detect patterns related to Earth's orbital mechanics. Looking forward, Earth's orbit isn't perfectly stable over extremely long timescales. Gravitational interactions with other planets, particularly Jupiter and Saturn, cause slow changes in orbital shape and orientation. The date of perihelion shifts gradually over thousands of years, moving around the calendar in a cycle that takes many millennia to complete. Currently, perihelion occurs in early January, but 10,000 years from now, it will occur at a different time of year due to a phenomenon called apsidal precession. When perihelion eventually shifts to occur during northern summer instead of winter, the seasonal intensity will change. Northern summers will become slightly more intense, receiving the benefit of both favourable tilt and close solar proximity. Southern winters will become slightly less harsh for the same reason. This won't cause dramatic climate shifts overnight, but over centuries and millennia, these gradual changes influence ice age cycles, sea level variations, and species distribution patterns. Earth's climate history over the past million years shows oscillations partly driven by these long-term orbital variations, known as Milankovitch cycles. Another implication involves solar energy reception. If you're designing solar panels or planning solar power installations, you might wonder whether perihelion affects energy generation. The answer is yes, but only marginally. Solar panels in the southern hemisphere receive slightly more energy during their summer than northern hemisphere panels do during their summer, due to the perihelion effect. But daily weather, panel angle, and local atmospheric conditions overwhelm this subtle difference. Still, for large-scale solar farms generating power across seasons, engineers include orbital variations in their energy yield projections. There's also a poetic dimension to all of this. The fact that we orbit an ellipse rather than a circle adds dynamism to our cosmic situation. We're not locked in some perfect, unchanging loop. We swing close and then arc away, speed up and slow down, dance through space in a pattern that's regular but not monotonous. There's variation, rhythm, a pulse to our motion that reflects the complexity and beauty of gravitational choreography. And consider this. Every planet in our solar system orbits in an ellipse, each with its own perihelion and aphelion, each with its own variation in distance from the Sun. Some planets have more elliptical orbits than Earth, experiencing more dramatic distance changes. Mercury, for instance, has a highly elliptical orbit, swinging close to the Sun and then retreating far away over the course of its year. This produces extreme temperature swings on Mercury's surface, far more dramatic than anything Earth experiences. Jupiter, Saturn, and the outer planets also follow elliptical orbits, though their distances from the Sun are so vast that the variations matter less for temperature. But for spacecraft visiting these worlds, understanding their orbital mechanics is crucial. When the Voyager probes flew past Jupiter and Saturn, mission planners accounted for the planets' positions in their orbits, timing the encounters to maximize scientific return and minimize fuel consumption. Our elliptical orbit also means that Earth's year, the time it takes to complete one full orbit, isn't perfectly consistent when measured by different methods. If you measure the time between successive perihelions, you get a slightly different number than if you measure the time between successive spring equinoxes, because Earth's orbit precesses slowly, and the equinoxes shift relative to perihelion over time. These are tiny differences, fractions of a day, but they matter for precise calendar calculations and have led to adjustments in how we define and measure the length of a year. All of these implications stem from the simple fact that Earth orbits in an ellipse rather than a circle, a consequence of how our planet formed and the gravitational environment of the early solar system. It's a reminder that nothing in the cosmos is perfectly simple or perfectly symmetrical. Everything has quirks, variations, complexities that emerge when you look closely enough. And those complexities, rather than being flaws or annoyances, are often the most interesting parts of the story. The details that reveal deeper truths about how the universe operates. So when you think about perihelion now, don't just think about the Sun appearing larger in January. Think about all the cascading effects, the connections to climate and space exploration, and ancient astronomy, and future orbital changes. Think about how one geometric fact, Earth's elliptical orbit, touches so many different aspects of our existence, from the seasons we experience to the spacecraft we launch, to the long-term evolution of our planet's climate. So here we are, at the end of our journey through space and time, having unraveled a mystery that hides in plain sight above our heads every single day. The Sun grew bigger, and now you know why. Not because of some catastrophe or cosmic anomaly, but because of the elegant, predictable mechanics of orbital motion that have governed our planet for billions of years. You're standing on a world that's constantly in motion, spinning on a tilted axis, orbiting a star in an elliptical path, speeding up and slowing down, swinging closer and then farther in an annual dance that creates the seasons, shapes the climate, and makes life on Earth possible. And most remarkably, you feel none of this motion. You live your life on what seems like solid, stable ground, completely unaware that you're hurtling through space on a dynamic trajectory that carries you millions of miles closer to the Sun and then millions of miles farther away every single year. This disconnect between reality and perception is one of the most profound lessons astronomy teaches us. What we see and feel isn't always the full story. The sun appears to rise and set moving across our sky, but in reality we're the ones spinning. The sun seems constant and unchanging, always the same size and always the same distance away, but in reality its apparent size varies throughout the year as our distance changes. We trust our senses because they serve us well in everyday life, but they weren't designed to perceive cosmic-scale phenomena. They mislead us, gently and consistently, unless we apply reason and observation to uncover deeper truths. And that's what makes knowledge like this so valuable. Understanding perihelion doesn't change your daily routine. Knowing that the sun appears larger in January won't help you pay bills or navigate traffic. But it changes how you see the world. It adds depth and richness to your experience of reality. When you look up at the sky now, you're not just seeing a sun. You're seeing a star that appears different sizes at different times of year, a visible consequence of Earth's elliptical orbit. You're witnessing geometry and gravity in action, playing out on a scale that dwarfs human concerns, but includes us in its grand pattern. There's wonder in this knowledge. There's awe in realizing that something as simple as the sun's size in the sky conceals layers of meaning about how our solar system works. And there's empowerment in understanding that you can grasp these concepts, that the mechanics of planets and orbits aren't beyond your reach, that with patience and explanation, the cosmos becomes comprehensible rather than mysterious. So the next time you step outside on a cold winter day, take a moment to look up at the sun. Don't stare directly at it, of course, but acknowledge its presence. Remember that it's closer to you now than it will be in 6 months. Remember that it appears larger, even if your eyes can't detect the difference. Remember that you're experiencing perihelion, a cosmic event that happens every year but goes unnoticed by almost everyone. And remember that despite this proximity, you're cold because of Earth's tilt, because of the angle at which sunlight strikes your hemisphere, because geometry matters more than distance when it comes to temperature. This is your planet. This is your orbit. This is your star. And now you understand their relationship in ways you didn't before. You've added a new layer to your mental model of how the world works, a layer that connects you to billions of years of planetary history and to the fundamental physics that governs everything from atoms to galaxies. If this journey through space has fascinated you, if you've enjoyed learning about the hidden mechanics behind everyday phenomena, then I invite you to continue exploring with me. Subscribe to this channel, because we're going to keep digging into the surprising truths about our universe, the counterintuitive facts that change how you see reality. Hit the like button if this video made you think differently about something as familiar as the sun in the sky, and drop a comment telling me what other mysteries you'd like to uncover, what other questions about our world and cosmos you want answered. Because the universe is full of these hidden patterns, these elegant mechanisms that operate constantly without our awareness. Every sunset is a demonstration of planetary rotation. Every season is a testament to axial tilt and orbital mechanics. Every star you see at night is a sun like ours, possibly with planets of its own following elliptical orbits, experiencing their own versions of perihelion and aphelion. The cosmos is vast and complex, but it's also understandable, governed by laws we can discover and describe. And the best part is that you don't need a telescope or a university degree to appreciate these truths. You just need curiosity, willingness to question your assumptions, and patience to follow the evidence wherever it leads. The sun grew bigger, and that simple observation opened a door to understanding orbital mechanics, axial tilt, seasonal variation, and the relationship between Earth and its star. One question led to answers that spanned astronomy, physics, history, and climate science. That's the power of asking why. That's the reward of not accepting surface appearances, but digging deeper to find out what's really happening. And that's what we'll keep doing together, exploring the questions that make us curious, following the answers wherever they take us, and emerging with richer understanding of this remarkable universe we inhabit. So thank you for staying with me through this exploration. Thank you for being curious enough to watch a video about why the sun appears larger during winter. Thank you for being willing to have your assumptions challenged and your understanding expanded. You're now part of a smaller group of people who actually know about perihelion and aphelion, who understand why tilt matters more than distance, who can look at the winter sun and see not just a light in the sky, but evidence of cosmic choreography, playing out across millions of miles of space. The sun just grew bigger, and now you know why. And that knowledge is yours to keep, to share, to build upon as you continue exploring the wonders of our universe. Keep looking up, keep asking questions. Keep seeking the hidden patterns that make reality far more interesting than it appears. Because the cosmos rewards curiosity, and there's always more to discover if you're willing to look.